Okay, let's get started. Thank you everyone for joining us today. Welcome to today's CNCF webinar, Highly Scalable Software as a Service Apps on Oracle Kubernetes Engine, Real Life Case Studies. I'm Jerry Fountain and I'll be moderating today's webinar. We would like to welcome our presenters today, Ram Kailasanathan, Senior Director of Product Management at Oracle, and Richard Bair, Senior Director of Engineering at Oracle. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of your fellow participants and all presenters. Please note that the recording and slides will also be posted later today to the CNCF webinar page at cncf.io/webinars. And with that, I'll hand it over to our presenters for today's webinar. Take it away, folks.
Thank you, Jerry. Hello, everyone. Thank you all for joining the webinar. This is Ram Kailasanathan here. I'm a Senior Director of Product Management within the Oracle Cloud Native team.
Yeah, and my name is Richard Bair. I'm a Senior Director of Engineering on the Oracle IoT applications and blockchain applications teams. And we are users of OKE.
Thank you, Richard. It's been a great experience working with Richard over the last year and a half. And folks, the goal of this webinar is to basically share how one of our marquee customers, essentially IoT apps and blockchain team within Oracle, have onboarded and scaled onto Oracle Kubernetes Engine, and really share all the learnings and best practices with this audience. The timing of it is fairly interesting in that, Kubernetes usage, if you take a look at the CNCF most recent survey, Kubernetes usage in production is skyrocketing. Compared to last year, Kubernetes usage in production has seen a dramatic rise. 78% of respondents are using Kubernetes in production, an impressive growth from compared to 58% last year. In that same survey, Kubernetes public cloud was the most preferred destination for using Kubernetes. And then also, there was one other takeaway with regards to containers. Containers are making their way to production environments. We saw 84% of respondents mentioning that they are using containers in production, an impressive jump from 73% into 2018. Before we jump into the core topic, I want to spend a couple of minutes really talking about a brief overview, providing a brief overview of our services. When you take a look at cloud infrastructure, Oracle Cloud Infrastructure, you should think about it as a bunch of high-performance servers, storage, and database services supporting millions of IOPS and scaling up and down based on your need. This is the true enterprise cloud you've heard mentioned. We don't focus on micro instances or VMs with time-sliced fractional CPU allocations. We focus on providing what businesses need to run real production workloads that may have to scale up as well as scale out, workloads that may require the reliability of a solid traditional hardware infrastructure in addition to the plan-to-fail approach of cloud, workloads that need low latency access to storage and networks. And we provide businesses with simple pricing and predictable costs. And if you take a look at this diagram here, we offer a whole gamut of cloud services, all the way from containers to data movement services to autonomous databases to events, streaming for AI ML workloads, and offer a whole slew of choices for our customers from a compute, storage, and networking perspectives. And our philosophy of building cloud services is fairly consistent. If you take a look at any of the services that I mentioned in the previous slide, it's fundamentally about delivering tools and services that are complete, integrated, and open. By that, I mean delivering tools and services, in the case of Cloud Native, everything from continuous integration to deployment to registry to orchestration, scheduling, management and operations when you start thinking about day two and beyond. And basically, we invest in and leverage open source technologies as the fundamental basis for portability. We actively participate in the community-driven open source forums, investing obviously in Kubernetes, Docker, and we have our FN open source initiative, which is for serverless and which is basically a serverless offering, the only serverless offering that is based on open source. And then we very actively engage with CNCF and a whole slew of other open source forums, as I mentioned before, through contributions and sponsorships. We have an active support for several other initiatives, including Helidon, which is a Java E initiative, and just to mention a few aspects there. And then moving on to the last pillar, managed services, we differentiate on quality of implementation, service and operational excellence in terms of providing a full and transparent management that is open source compatible, that's standards compliant, and you can essentially deploy all your applications onto Oracle Cloud Infrastructure that is essentially an enterprise grade, that offers an enterprise grade performance, security, high availability, and governance. When we actually sat down really talking to several of our enterprise customers and startups who wanted to deploy their applications onto Kubernetes, we did a number of these customer requirements gathering, sitting down with obviously real customers, but also leverage CNCF survey as well. One thing that really came out was Kubernetes is very important, is essentially think of it as a hub for modern cloud native way of developing applications. But Kubernetes by itself is not everything, right? I mean, customers consistently mentioned about a number of these observability tools, including logging, monitoring, and also mentioned about service meshes and additional networking technologies, storage interfaces, and most importantly, security and compliance, in addition to the core Kubernetes offering. And so that has become essentially our primary sort of data point for building additional services, offering additional services on top of Kubernetes. And when you think about, so in the previous slide, I talked about what we learned from customers. And in this slide, I'm talking about Oracle Cloud Infrastructure, Cloud Native, and Developer Services portfolio. We start all the way from, our customer is front and center in all our, from day one design thinking. And it starts from easy to start and adopt. We offer a console that's very intuitive and easy to use. And then we offer a whole slew of additional capabilities for you to try a bunch of things before you start serious application development on Oracle Cloud. Then we get into the core application development aspect. Here, we are living in the world of APIs. The API design is very important, and cloud. We offer simple to use services such as Cloud Shell, Resource Manager. Think of it as an automated services for infrastructure as code, and then obviously source control and container registry are all very important aspects of this aspect of the overall development lifecycle. Then when we get into deploy, obviously we're going to share a bunch of things about Kubernetes today. But in addition to Kubernetes, we also offer, as I mentioned before, functions and streaming services as well for some of the workloads that might want to choose these technologies. And then when we go to day two and day two and beyond, we start looking at a number of these observability tools, including monitoring and logging. And then we also offer event service, notification service, and email service for a bunch of these use cases. Being an enterprise-focused company, we have, we think about security and compliance from day one, and that's sort of reflected across all the services that we've built thus far. Now, before transitioning, I want to sort of say that, as I mentioned before, Richard and I, we've worked together for the last year and a half, very closely. And IoT Apps is one of our marquee customers of OKE. And in the second part of the presentation webinar here, Richard is going to take you through a bunch of learnings from a customer's perspective. Thanks, Richard.
All right, thanks, Ram. So yeah, I'm really excited to do this presentation, and hopefully some of the content that I have here will be useful to the folks who are on the webinar and those who are watching online. We've been, as Ram says, we've been using OKE now for a little while, and our team actually had some experience with some of the other clouds as well. And so there's a lot of things that we've learned over the last few years, and hopefully some of this will be useful for you. So today, I really have two items on the agenda. I'm going to talk a little bit about the IoT project itself so that you have some context for what we're doing. And then just as far as how it'll be useful to understand then how we're using Kubernetes. And then I'm going to be talking about 4 lessons that we've learned through our own sort of failure and experience. So the first thing that I need to do is just kind of, brush up my bona fides here. We are running north of 17,000 cores across our Kubernetes clusters. And we have more than 50 different OKE clusters that we are running workloads on. So we've got some pretty big clusters, and we have a lot of clusters. So we're looking at scale in 2 dimensions here. We're talking about scale vertically and horizontally. And there's a lot of things that you have to solve when you're facing those problems. And so that's kind of the genesis for what we're going to be talking about today. Now, the Internet of Things products at Oracle, we have their SaaS applications. We have 5 different SaaS applications that we sell. And on the blockchain application side, we have one for supply chain management. It's called Track and Trace. And each one of these applications is essentially designed in the same manner, and all of them are using OKE. So as Ram mentioned, we started using OKE around late 2018. I noticed on your slide earlier, Ram, that there were a lot of people who were, let's say there were 2 interesting categories on there. One was the number of people who were reporting that they had some sort of cultural change that they needed to make on their team. And there was another category where it was the number of people who needed training on OKE. And the fascinating thing was that the percentage of people reporting that in 2000 in the March or the earlier survey was like 0. And the ones reporting that in the later survey were substantially higher, which sort of indicated that they're kind of in a transition period in late 2018 towards production. And that was certainly our experience. Our products have been out there since about 2016. We were on a couple different clouds inside Oracle before we came to OCI. And internally, previously, we were using Docker already for development and for testing. But when it came to production, we were deploying on VMs. And so when we made the transition to OCI, we wanted to change the way we were doing things so that we had the container workflow from development all the way through to production. We wanted to really benefit from what you get when you're using those containers through that entire workflow. So we decided that we were going to commit to using Kubernetes on OCI. So then the next question was, well, are we going to do our own bespoke Kubernetes install, or are we going to use OKE? And we did some research and we tried out OKE, and it was super easy to get started with. And so we said, okay, let's do it. We're going to use OKE and OCI for everything we do, from development, testing, staging, and production. We literally don't have any other virtual machines that we use for anything that's not somewhere in OKE or on OCI. Every developer on our team has some quota on a development OKE cluster, and all of our automated SQE tests are run on development or staging clusters. one of the principles that I had was I wanted the development to be as close to production as possible, because my team is responsible for making sure that everything runs in production, and really want to make sure that if we're going to find problems, we're going to find them earlier rather than later. So being able to do development on the same environment that we're going to go into production on is really important to us. And that strategy's worked really well for us. Previously, like I said, we were using Docker, which was great for development, but then when we got to production, we were running on virtual machines and using other PaaS services that we didn't have in development. And so we would find things in production, which was not really neat. So we're really happy with being able to use this stuff in development as well. And I should also acknowledge that now that we have a year and a half under our belt here, that using OKE makes Kubernetes a lot easier than it would have been if we were running it ourselves. And the OKE team, the really essential thing for anybody who's done this in production, you know this is true. The essential thing is not that there's another team providing you a service. The essential thing is that the team that's providing a service does it well. And the OKE team does a really good job providing their service. We just don't run into problems with their hosting. It's worked really, really well for us. So we're using OKE all the way. So let's just go ahead and dive into some of the lessons that we've learned, like I say, through failure and experience, which is the best teacher. So the first thing is this, lesson number 1, things die. Operating anything at scale requires careful attention to the architecture and the design to make sure that everything is highly available. And Kubernetes provides us all of the tools that we need to be able to be highly available. Kubernetes gives us these concepts of deployments and stateful sets, which Kubernetes uses to automatically maintain a configured number of replicas. So if we say that we need 10 web servers, it's going to try to make sure there's 10. If one of them dies, Kubernetes automatically tries to bring one back up. Honestly, when I was evaluating Kubernetes to begin with, the fact that it helped do this was really powerful to me. It meant that it wasn't something that I had to do myself on top of VMs or some other way. Kubernetes had this built-in support for bringing systems back up if they die. Kubernetes monitors every pod's readiness and liveness. It uses health checks, figures out whether something is healthy or not. So even if your container's running, but it's not healthy, it can report that. Kubernetes will kill it and get you a new one. Those sorts of things are really handy in production for making sure that your system stays alive through all the bumps and bruises that happen in life. Kubernetes also gives us a declarative way to say that pods should be spread across multiple availability domains. So even if we lost an entire availability domain, we would be able to survive that kind of failure. And we have, these are not just academic things. This happens in real life, in real clouds. And it's really a great feature that we're able to make use of. Kubernetes also gives us a way to declare how many pods in a deployment or a stateful set can go down at once before we lose availability. And this is called a pod disruption budget, and it's another really great feature that Kubernetes provides and makes some things a lot easier to automate, because you can tell Kubernetes, hey, I want to take down these 5 nodes in my node pool. And it goes, okay, I'm going to go take those down. But then it looks at your pod disruption budget and says, I realize I can't take all 5 down at once without hurting your availability. So I'll just take down these 2 that I can right now. And then once those are back up and those containers are back up and running, I'll go move on to the other pods that I can take down. And so that kind of automation is really handy, because there are many times when you do need to go through your entire fleet of nodes and recycle them, which we'll talk about in a bit. So the pod disruption budgets are another great feature that Kubernetes gives you. So, okay, Kubernetes provides me all these tools that I need for a high availability. And, a lot of people, when they come to this, they're used to programming, like if you're new to the cloud, right? you're used to programming on your computer doesn't die that often. Maybe you've even had a few workstations. It's like, yeah, every now and again they die, but not that often, right? So why is it such a big deal that everything is highly available? And the answer is, it's a little bit more complicated. There's a lot of reasons why a pod may die. And some of these things are not, it's not like instability in the cloud. That's not it. What it is it's architectural benefits that you get if you design your system to rapidly kill things. Probably people on this call are familiar with the concept cattle, not pets. So there's a lot of reasons why you may have a container or a pod die. So a pod could die if, for example, it just becomes unhealthy. Certainly all of us who write software are familiar with this. You know, you ran out of memory, or you had a core dump, or something, something went wrong. System just stopped responding for some reason. All those could be reasons why it became unhealthy. And the easiest thing to do is to just, reboot it, which is essentially killing the pod and getting a new one. Somebody could have killed it manually. Kubernetes provides controls for deleting pods, and if somebody deleted a pod, then it needs to come back up. The cluster could have been scaled out. When I say the cluster, I mean the Kubernetes cluster itself. Perhaps that got scaled out. Maybe you had the 10 nodes in your cluster before. Now you have 20 nodes. All of your pods are still on the original 10 nodes. Well, you just added 10 new ones. You would like to rebalance your workload. That involves deleting pods on one node and bringing them back up on another node. So that's another reason why your system might go. And that's what I mean by architecturally, you have benefits if you support this sort of high availability concept. So you should embrace that and just really deeply embrace the idea that any pod at any time could go down. If you write your software that way, then it enables things like rebalancing clusters to be a trivial operation. It's also possible that the node, the virtual machine that your pod on itself, will die. And you might have a fair number of those. And this can happen under normal circumstances again. For example, the virtual machine that is that node might need a new image. In our team, we upgrade those images quite regularly with the latest patches and everything else for security reasons. So we're regularly going through and recreating all of our nodes, and that means pods are dying and getting rescheduled somewhere else. And our customers are completely unaware of that because our system was designed to be highly available. You may find that the kubelet needs to be upgraded, and that requires recreating the node. And sometimes things just stop working. We found that with some virtual machine shapes, sometimes the virtual machine would just be unhappy, and the recourse was to restart that virtual machine or to delete that virtual machine and get a new one created. All those things are just kind of normal and common, and if you've designed for a high availability, then they become easy, and you get to reap the benefits of that. So that was the first lesson we learned, is that things die, you need to be prepared to deal with it, and it's totally common. It's not a once a quarter thing, it's not a once a year thing. If you've designed for it, you can actually use that to your advantage, and you'll experience it a lot, and it won't cause you any problems at all. In fact, it's just normal part of your daily business. Okay, so lesson number 2 was kind of, I don't know, this year I'm starting to feel like I'm a little bit older, and so I had a little joke here. So yeah, so persistent pains, it's not just something you get in old age. So Kubernetes has this concept of a persistent volume. And we usually just call this a PV. Each PV is backed by some actual storage volume. Typically, it's a OCI block storage volume. And those block storage volumes are awesome. They have a lot of great features to them. You've got the ability to do immediate snapshots of it. So for example, if you're backing up data on that thing and you take snapshots, it's fast and really cool. So the things that we've been able to do with those persistent volumes, those block volumes. But there's kind of a dark side. We found that there are some actual issues if you overuse persistent volumes. So the first time that you come to something like Kubernetes, you might be, in your mind, you might have the mindset of each one of my pods is like a virtual machine, and every virtual machine has a block volume. So I will have some kind of persistent volume associated with every pod in my Kubernetes cluster. But that runs into a bunch of different problems, and you really don't want to go down that road. You know, in our experience, we found that we were using persistent volumes too freely, and it was causing us a lot of problems. So here's 6 of sort of problems that we ran into. One problem is just sort of the mechanics of it. So those block volumes don't come for free, and your container is not a virtual machine. There are actual virtual machines underneath of this whole thing, and those are the nodes that make up your Kubernetes cluster. And each one of those VMs has a limit on the number of attached volumes that they support. So this is kind of really important, because it means that if my underlying node only supports, let's say, 32 mount points for block volumes, then I cannot run, if every single one of my pods had a persistent volume, I would be limited to 32 pods per node, which is kind of a shame, because nodes can really support more than 100 pods. So unless your pods are using a tremendous amount of CPU, what you would find is that you were limited in scale, not by CPU or memory, but by the number of mount points. And so that can end up being a problem for you. The more persistent volumes you use, the fewer pods you're going to be able to run per node. So that was the first thing that we found. We also encountered some bugs, as you'll find in any software. And we found that sometimes our persistent volumes got mounted as read-only. And there's I'll talk about in a bit, there's a fix for this. But it's just, I think the underlying principle here is that persistent volumes are just another piece of technology. And the more pieces of technology you employ, the more likely something's going to go wrong. So limiting that extra piece reduces the number of potential issues that could go wrong. Another issue is that persistent volumes are per availability domain. So in a availability domain is like an availability zone in AWS, right? So you go to some region and you've got 3 distinct data centers. Each one of them is a different AD that are all part of the same region. And these block volumes are part of a particular data center. And so, but pods are not. And your Kubernetes cluster spans all 3 availability domains in a region. So if a pod moves from one availability domain to another, then it'll fail to attach to the persistent volume that it left behind. It's kind of like getting up to move states and finding out you left your pet behind or something. You moved to a new availability domain, but your data was left behind and it wouldn't attach. So this was a problem that we ran into, but there's a new driver in Kubernetes called CSI. It's a plugin model for persistent volumes, and OKE now has implemented that, and it's designed to help resolve this exact issue. So hopefully issue number 3's gone away at this point. We're not running into it right now, but this was a problem that we had encountered previously. Another issue we had, which is kind of specific to OCI, I guess. I mean, every cloud has these sorts of limits, but I'm not up on what the specific limits are for everybody else. But in OCI, persistent volumes have a minimum size of 50 gigabytes. And the problem that we had was that this was just too expensive for development, because we have, we have a big development team, and we're building a lot of stuff. And so we have a whole lot of these persistent volumes that we were creating, and it was just a lot of disk, even though in development, we only needed like maybe 500 megabytes for each one of these persistent volumes. We had to get them in a minimum 50 gigabyte slice. In production, this isn't a problem for us because our data storage for Internet of Things is much larger than 50 gigabytes. So it really wasn't an issue in production, but in development, it was an issue for us. So what we ended up doing was setting up our own Ceph cluster, which is kind of a off-the-shelf block volume system, if you will. So we got some of the dense IO bare metal machines from OCI, and we set Ceph up on that. And it's able to give us persistent volumes that are a lot smaller in size. But I don't really like that solution because as cool as dense IO is, there's extra stuff to maintain there in development, and it's different than production. And that's one of my goals is to try to reduce that. So that was another issue that we ran into with persistent volumes. We also found that there is a limit to the number of persistent volumes that you can have. And this has, again, CSI should have addressed this, and we haven't seen this problem recently. But just so that you're aware of it, these things are sometimes deeper than what you look at on the surface level, right? The problem that we had was that once we exceeded a certain number of block volumes, there was so much API traffic that was going to the block volume service that the block volume service was rate limiting it. And that was leading to attach errors on the Kubernetes side. So Kubernetes was like, oh, I can't attach this block volume because I can't talk to the block volume service because you've been rate limited. So that was another issue that we ran into. That happens because the old flex volume implementation on Kubernetes wasn't doing any caching. And so it would basically, periodically Kubernetes asks the kubelet and it says, hey, I need you to go run a report basically and find out if which persistent volumes are still attached to you and which ones are not, so that I can update my database on the Kubernetes control plane. And so when it would do that, it would go to the block volume service and then it would get rate limited. Even though we weren't reattaching or anything, it could just be sitting there idle and run into these problems. So CSI is the new implementation. It replaces the flex volume. And in this implementation, there's caching and things like that so that you don't run into those problems. But this was another issue that we had run into. And there was one other thing that was kind of interesting is that if you're doing IO intensive tasks with block volumes, they're a lot slower than say a local disk or something like that, unless you have really large block volumes, because the number of IOPS that you can get on an OCI block volume is really high. And block volumes also, like I said, they're really cool because of the snapshotting that they do, and also everything's encrypted at rest and everything else. But because those block volumes can be sliced from large to small, you get less bandwidth when you go with the small ones. So if you're doing lots of little persistent volumes, then you'll find that the IOPS there is a lot less than what you'd find on, say, a laptop. Whereas if you're doing large persistent volumes, like if you're storing a ton of IoT data, then you'll find that the block volumes are really fast. Even though they're network attached, they're really fast, they're really good hardware. But you have to have large block volumes. So again, when you're talking about testing and things like that, if you're doing small block volumes, you would find that there's kind of a disadvantage on that when it comes to performance. So you might think, well, okay, persistent volumes are all bad. What do we do? So there's a few. First off, if you have to have a block volume or a persistent volume, I should say, for storing customer data, then you should use a PV. It's not like they don't work. They work really well. They work right out of the box. Everything just works. The problem is when you have lots and lots and lots of little PVs. That's when you start to run into some scale issues. But persistent volumes don't have to be backed by a block volume. You can also back them with what in OCI is called FSS, which is basically NFS for OCI. And we actually make use of this for some of the things that we do, and it's really cool. So one of the things that we do is our developers want to have access to a heap dump if the pod runs out of memory. Well, typically one of the problems that you'll run into is that when your pod runs out of memory, it reports to Kubernetes that it's unhealthy. Kubernetes deletes it, and a new one is created in its place. And when that happens, whatever ephemeral storage you had associated with that thing goes away. So you might think, wow, I need to attach a persistent volume to this thing so that the heap dump will be persistent, or crash dump or whatever will be persistent across pod restarts. And you'd be right. But as I mentioned, having one of those on every single pod is going to cause a problem. So instead, what we found was that we could create a persistent volume that was backed by FSS. So we have one big shared file system. We attach it to all of our pods. And then when the pod does a heap dump, either because it ran out of memory or because we manually invoked a command to make it a heap dump, or if it's going to do a crash log or something like that, it gets written into this FSS-backed persistent volume. And then we have completely other jobs running in Kubernetes that go through that FSS and they find these volumes or these dumps, and they process them and turn them into something that we can share with a developer and all that kind of stuff behind the scenes. So having a shared file system for that is really cool because you're able to get multiple pods all using the same underlying storage unit. And FSS scales with your usage. You pay for what you use. So unlike a block volume where you say, okay, it has to be 50 gig minimum, with FSS, it's like, well, however much you use, it just keeps scaling out for you. So that was one use case that we found that was really neat for persistent volumes in Kubernetes. And another point that I wanted to make about something that we learned was how to deal with logs. So one of the main problems that we ran into early on, it seems silly, but it's true. It was just our logs. We would be logging things to disk because that's the default behavior of most log systems. And when we would log it to disk, eventually the log file would get so large that it would fill up all the space on the node. And when you, so the way that Kubernetes and Docker works, right, is that you have your node, which is your virtual machine. It has some block volume associated with it, which is your boot volume, or maybe some additional data storage place that you have on there, right? And then you run a bunch of containers on there. And each one of the containers is, when you write to a non-persistent disk space, like in the ephemeral storage space of your container, it actually writes it onto the node itself. So the problem that we were running into was that one container is generating tons and tons of logs, filling up the disk on the node, and eventually the node runs out of disk and dies, and all the other pods that were running on that node suffer as a consequence of that. So what we learned was that logs need to be given an explicit size and rotation so that when they start to, so that they can't fill up space. That's the primary thing. Because the first thing that we did when we saw that was we were like, oh, we need to get those logs off of the node's hard disk. So we will attach a block volume to this thing that it can write its logs to. But then we found that that was running into all these other problems with having too many persistent volumes. So we're like, okay, what else can we do? So what we ended up doing is we already have a Kibana Elasticsearch ELK system set up that we're sending all of our logs to anyway. So actually the only logs that we needed locally was just what we needed as a buffer until we could send it off to our logging system. So we scaled down the size of potential logs to a small number, like 100K or 250K or whatnot, and then have a rotation on it. So we just have a couple files rotated and that's it. And then it's just as a buffer that we can then send everything off to the ELK servers where we can actually inspect all the logs for our entire system. And every pod in Kubernetes can have ephemeral storage. It's super great for small disk usage. You'd never use this for storing customer data. And all the data that's in ephemeral storage just vaporizes whenever the pod goes away. So it is ephemeral. It doesn't last. It's not persistent. But if all you're doing is storing some buffer for some little things, or you just need a little scratch space or something like that, just use ephemeral storage and don't even bother with any type of persistent volume. Okay, so that was basically lesson 2. Lesson 3 is a little faster. This was just about limits. So Kubernetes has these concept of like a request and a limit. So every pod can say what the minimum resources are that it needs, and it can also say what the maximum resources it needs are going to be. And then Kubernetes uses that information to schedule which node you're going to run your pod on. And requests are good because you're able to make sure that your pod has at least the minimum resources, the minimum memory or CPU or whatever it is that your pod needs. And the limits are good because it prevents one pod from stealing too many resources from other pods that are running on the node. And Kubernetes does some other things, like if there starts to be pressure, like say it starts to running out of memory on the node, it's going to go look and see which pods have limits and requests, and it's going to take that into account to decide which pods to evict and reschedule somewhere else. So, when we first got started using Kubernetes, we never put requests and limits on anything. We just didn't, we just didn't. And we started seeing pods getting evicted all over the place. And we found out that it was because resources started to get overused, and then Kubernetes was evicting pods, and it didn't have any guidance on what to evict when or where. So for our particular workload, it's very much memory intensive. So we set the request and limit to be the same for memory so that we have dedicated memory for each one of our pods. But CPU for us is totally over provisioned. So we set the request to something really, really small, and we don't even bother with the limit because, use as much as you want. Or we set the limit to something high, like, so it doesn't use all CPU on the system, but it's not as strict, right? Because I want to be able to over provision CPU on that thing. So, Kubernetes gives you the ability to do this. And if you make use of this, then it actually is really helpful to you because it gives you a little bit better control over what gets scheduled where and what happens when you start running into your memory limits. And I think for us, the biggest deal in stability was getting our memory just right. When we set our memory, we had to make sure that it was set large enough to account for, we do a lot of Java, so we had to make sure we had enough JVM memory and enough OS memory, if you will, system memory for the stuff that's going to run. Same thing if you're running Go or something else, you have to just make sure to get those sizes right. And if you do, then we found that things got really stable at that point. Okay, last lesson, lesson number 4. Monitoring is absolutely essential. We would have absolutely no chance of running anything at scale without good monitoring tools. And we invest a lot in making sure that all the monitoring is working really well for us. And it's something that we're continually working on. So every one of our OKE clusters runs a Prometheus, which gathers all the metrics together. We have a global Thanos, which is basically it's like it distributes Prometheus queries to all those little Prometheus servers running on all the clusters. And it gives us a single place that we can go and get metrics for all of our production systems. We have, similarly, we have a single Kibana and ES cluster for all of our logs. And so we have a single place that we can go to look for logs across all of our systems. We use the alert manager, which is the technology comes with Prometheus, in order to raise our PagerDuty alerts. So it's based on Prometheus data and Kibana data. We'll raise PagerDuty alerts. And that's how we are able to proactively address issues in the cluster before it becomes an issue for our customers. One really important point is this health check. So in addition to the Prometheus, we have this health check, and the health check is used by default by Kubernetes, but we add a lot more to that health check than just what Kubernetes makes use of. And we use that as input also into our, the health check data also goes into our Prometheus system so that we can do some really advanced visualizations that are useful for us for knowing what the health of our system is. And the important point here is that initially you'll be doing monitoring probably for your core infrastructure, but the real value comes when you're doing monitoring also for your application level monitoring. So I think that's the important point. So here's just a couple screenshots of some of the dashboards that we have. We have one for global alerts where you can go in and select any one of our environments. You can select the type of cluster which is something that it's a taxonomy we use for our system. It doesn't apply to everybody. And then you can pick a specific cluster, or you can say all clusters, and you can give it a time range, and it'll tell you how many alerts you had during that time and what kind of alerts you had and so forth. We have some dashboards that show us the health of particular clusters, or again, all clusters, or specific VMs and specific availability domains, different ways of slicing and dicing it, but the dashboard will show us how many nodes we have in this cluster, how many failed nodes, and where they're at, what the health of them is like, and so on and so forth. This one is specific to our service, and you see all those little green boxes on the left? Those are like the application level concepts of are different things that I depend on as an application, up or down. And this has been really, really useful for us. And it comes from our advanced health checks that tell us in more detail what's going on in a particular service instance. So that when we're running into a problem, it's very easy to see because it comes up red. And then we have some of the normal gadgets that also come with Prometheus, where we can see the CPU usage for all of the different pods for this service instance, all the memory being used by these. Also the HTTP error rates are golden signals that tell us, what's the customer experiencing on this service instance. And all right, so that's our 4 lessons that I wanted to share with you today. First one is that things die, so design for HA from the beginning. The second one is to use your persistent volumes wisely. They can be really, really useful, and we use them a lot, but they do come at a cost. So don't just think that you can use persistent volumes blithely. Third is limits and requests really help to make things stable. And the fourth one is that, like as somebody who's responsible for watching this stuff in operations, my background, I was an application developer. Then I joined Sun Microsystems, and I was an architect on a Java platform. And then I came to work on IoT and SaaS applications. And I did not appreciate, until I was in this position of running things in production on the cloud, I didn't appreciate how crucial monitoring is, but it truly is crucial to your applications. And you want to make sure that you've got really good monitoring in place for the stuff that you do. So given that I've been using OKE and Kubernetes now in production, all my customers are running on this thing. Do I recommend it? My answer is yes. Slide's a little bit long-winded, but the essential point is there at the bottom. The higher up the stack, the better. We're in the business of delivering Internet of Things, SaaS applications. We're in the business of delivering supply chain management applications. The rest of the stuff that we have to do in order to make that work is just sort of the underpinnings, but it's not necessarily something that we want to be investing a huge amount in. So the higher up the stack we go, the better. And OKE lets us live a lot higher up the stack than any of the other technologies that we had available at our disposal. So the OKE team's done a fantastic job of supporting us, and their management of their system has been solid. And so it really has taken a big weight off of our shoulders in terms of how to manage these environments. So it's been a really good experience for us. Definitely recommend it. And with that, there's some resources. You'll have these slides afterwards, and I want to stop now so that we can open things up for questions and answers. Thank you.
Okay, thank you both for a wonderful presentation. Do you have any lessons on security in OKE?
Yeah, so there's a couple. So first thing is that we did not accept any kind of code from customers. So our initial concern was, I think common to a lot of people running on these clusters, is if I have a security breach in one of these containers, what can somebody do? And they can do a lot. So one of the ways that we secure our system is by not accepting any type of code from customers whatsoever. And when I say code, I don't just mean like Java or Python or something. I mean, no SQL, there's nothing that you can feed to us. And if you do feed us something like an image or something like that, we run it through, it's outside of Kubernetes, right? It has nothing to do with Kubernetes, but any inputs that come through end up going through antivirus software and all that kind of stuff, so that we can make sure that the stuff that's running in there is solid. The other thing is that you can use something like Calico as, and this is kind of common for all the teams that are building on to OKE today inside Oracle. You can use something like Calico in order to restrict which pods are able to access which pods. So Calico gives you a way to do network security at the Kubernetes level. And so that's another technique that can be used to.
In addition, OKE also supports pod security policies.
Yes.
And, supports private worker nodes. And also you get all the benefits of the core security and network isolation that you would get, adopting OCI in general, not specific to OKE, but all the OCI related security features you just naturally benefit from.
That's a great point. So like, for example, private endpoints on the database. So you can set up when you create your Kubernetes cluster, you create it inside some virtual cloud network. And when you set it up inside there, your first line of defense is, of course, all the OCI security boundary that you get from security lists and things like that, and your subnets and such in your VCN. But you can also use like the private endpoints on ATP or some other services, which will basically give you the ATP service inside your VCN so that it's not routable externally at all. So then, you have this nice secure bound.
Also, there was a question on chaos engineering, Richard. Anything that you can share from a customer perspective?
Good question. So our team is, I'd say, sort of adolescents when it comes to chaos engineering. When I say our team, I mean the IoT team. So at the moment, we're doing most of our chaos engineering is manual. We'll set up a cluster and then we'll go take down a particular all the nodes in an availability domain and see how our system responds, things of that nature. We're not quite at the point yet where we've automated it, but it's definitely something that we are planning on doing in the next year.
Yeah, and we also see some interesting startups offering chaos engineering as a service. And from a product standpoint, we're looking to really work with some of these startups to offer this as a marketplace service. And that's definitely something we are looking into.
Okay. Do you recommend any databases in Kubernetes?
So I personally don't recommend running any databases inside Kubernetes itself. I guess it depends on how you define a database. So we run Elasticsearch inside of our Kubernetes, and we run Oracle NoSQL inside of our Kubernetes. I guess both of those could be considered databases by some. But I'll be honest with you. So I'm going to be totally honest. When I was at Sun, Oracle database was very difficult to set up and administer. And ever since Oracle Cloud came around, it makes Oracle database so easy. It's so easy and it's so powerful that the Oracle database is my go-to for a database. And I'm not saying that as like an Oracle guy, even though I'm an Oracle employee. I'm telling you that as an engineer, right? My experience with the Oracle database, we use the autonomous database ourselves. And it's just so much easier than it is hosting your own database inside Kubernetes. It's so much easier and powerful that I would definitely look at that as a first option before I looked at anything else.
Did you move out from Flannel to Calico for production clusters?
We have not yet, but even our use of Calico was not going to replace Flannel. It was just going to be used for the networking level stuff. But we're actually looking at another project also, I think it's called Cilium, which also does the network level security stuff. But we haven't moved our production clusters onto it yet.
Okay.
Yeah, from a product perspective, we're also looking at some of these options to offer this as a service as well.
Did you use Helm chart for managing packages or other tools?
That is a great question. In fact, I would like to do an entire presentation on that sometime. We do not use Helm. We started off with Helm 2. We were like, let's try to make use of this. There were various reasons why we didn't go with it. One of them being that config maps didn't get updated properly, and there was some bug, and I dug into it, and it was one of those, it doesn't really work that well. Maybe in Helm 3 it'll work. there's a much longer answer on this though. Deploying applications on Kubernetes is way more than just deploying some Kubernetes YML files. And Helm is essentially deploying Kubernetes YML files. That's part of the story, but it's not the whole story. Especially if you're trying to do something like blue-green deployments. I mean, you can't just apply YML files. There's a whole orchestration thing that has to go on here. Spinnaker is supposed to address some of that, but I've had some problems with Spinnaker. I'm not really sold on it, even though I want to be sold on it. I'm not really sold on it. So I think there's a big area here where, in our experience, there's room for better solutions for deploying applications on top of Kubernetes.
Okay. Well, thank you both very much for a wonderful presentation. That's all the time that we have for today. As I said earlier, the presentation and slides will be available on the CNCF website later on. I'd like to thank everyone for joining us today and for our presenters today. Everyone, take care of yourselves, stay safe, and we'll see you next time.
Thank you, Jerry.
Thanks.